Greetings, I'm Maite Maldonado, and along with Bill Landing, I'm one of the co-chairs of the GeoTraces Data Management Committee. We're so happy and excited to welcome you to this webinar on the release of the 2025 GeoTraces Intermediate Data Product. This is the fourth intermediate data product from the International GeoTraces Program and includes tens of thousands of new data points submitted by over 700 scientists from 35 countries. The GeoTraces Intermediate Data Products combine quality control, reliable data for trace elements and isotopes, along with information on biogeochemistry, physics, biology, and ocean atmosphere interactions. These intermediate data products serve as powerful and practical tools for scientists and educators, as well as policymakers. I'll now ask Elena to play a short video that gives us a brief and general introduction to the GeoTraces program, what we do, why we do it, and how we do it. Elena, if you could please play the video.
Let's imagine that we are able to see our future in the oceans. Does this idea seem surprising to you? And yet, marine environment shelters a large amount of information which, once decrypted, gives us the magnitude of mankind's impact on the ecosystems. So it's possible to anticipate the amplitude of global warming and prepare tomorrow's world. This is the mission the GeoTraces program contributes to since 2010, bringing together scientists from 35 countries. Given the sheer size of the oceans, they had to unite their efforts to develop technical solutions essential for detection of chemical elements in the seawater. These elements include nutrients essential for marine life, such as iron, zinc, manganese, and copper. Toxins that accumulate along the food chain, such as mercury and lead, or radioactive elements. GeoTraces also measures the indicators that provide information for improving climate models such as beryllium, radium, thorium, and rare earth elements. As an example of the complexity of this process, quantifying the iron in a sample is like measuring the amount of metal present in a paperclip dissolved in 30 Olympic swimming pools. To this end, oceanographers in the GeoTraces program are organizing major scientific cruises to explore the widest reaches of the world's oceans. These expeditions can last more than a month, during which experts carefully collect samples using clean techniques and specialized equipment throughout the depths of the ocean. The extracted samples are then transported to home laboratories before being analyzed using results which are assessed and shared. This valuable data will complete a global atlas showing the distribution of multiple trace elements throughout the ocean. Now everyone can benefit from this freely available information and use it to answer questions about our changing world. As you can see, GeoTraces' mission is a major challenge in line with the current environmental goals, in which we can all take part and change the world together.
Thank you, Elena, for that. Just a reminder that that video, along with lots of other useful information and resources, is freely available at the geotraces.org website. We want to offer our deepest thanks to everyone of the 700 plus scientists who are collaborating in the GeoTraces program and who have contributed data to the GeoTraces Intermediate Data Products. Their commitment to the highest standard and data quality and reliability has made the intermediate data products possible. We also want to acknowledge the tremendous volunteer efforts of the co-chairs and members of the Standards and Intercalibration Committee, the Data Management Committee, the GeoTraces International Data Assembly Center, and the Scientific Steering Committee, who have had a tremendous dedication to the program over the last 20 years since the start of the GeoTraces program. Thank you all. Finally, we want to acknowledge the enormous contribution from Elena Max Ferrer, our executive officer at the GeoTraces International Public project office. Elena is responsible for the public face of GeoTraces and for keeping everything running smoothly with support from the Lagos laboratory in Toulouse and the director, Catherine Jendal. Regarding our collective behavior for this webinar, please remain muted. Please use the chat function to submit questions and indicate the speaker's name. We'll try to address them during the Q&A period at the end. In all cases, the speakers provided a short video presentation to facilitate conducting this webinar. Depending on their respective time zone, they have offered to zoom in and hopefully be available to address your questions at the end. I know that at least Cecile Guieu and Zhenjian Li are here today. Now with the show. So our first presentation today is from Professor Rainer Schitzzer. Rainer Schitzzer is a professor at the Alfred Wegener Institute in Germany. Rainer has had a very distinguished career in oceanography and is probably most well known to this audience as the force behind the Ocean Data View and WebODB. Rainer is a former co-chair of the GeoTraces Scientific Steering Committee and the Data Management Committee. He has been instrumental in generating the GEOTRACES Intermediate Data Products, and we'll talk today about IDP 2025, what it contains, and how to access it. Elena, if you don't mind to play the video, please.
So hi everyone. In my presentation, what I want to do is to show you what the new IDP 2025, what it actually contains and how you can access it. And as before, the IDP contains of two parts: digital data, this is the core of the whole product, and a visual component, the GeoTraces Atlas. And again, as before, the digital data has 5 separate data sets. The core, again, the seawater discrete sample data, seawater sensor data, aerosols, precipitation, and cryosphere data. And I will quickly go through them and show you what's inside. Cryosphere data is maybe the smallest of all. It just has a small number of stations in the Arctic, and it contains ice and melt pond data for 41 TEIs. And since the last IDP, a moderate number of new values for these parameters here on the right are entered. Precipitation, that's rain and snow data for 94 TEIs, that actually has seen no change since the last IDP 2021. Aerosols, this is a global database. There is quite a number of new cruises, 6 new cruises, 113 new stations, making now a total of over 400 stations. The new ones are in red, some Southern Indian Ocean, North Atlantic, some new data in the Pacific. Seawater sensor data, that actually contains the high resolution and the vertical downcast sensor data, which we think complements the actual TEI data and helps their interpretation. This global data set, it has quite a number of new cruises listed here on the right, about 950 new stations, a total now of more than 4,800, and the new ones are highlighted in red. Some Pacific data, a few in the Arctic, some Indian Ocean, and some in the Atlantic. If you look at the Southern Ocean, there's quite a big added contribution in the sensor data set. And finally, which I would call the crown and the core of the IDP, the seawater discrete sample data, where we now have almost 400 TEIs. And there's a large number of new cruises in this data set. There are more than 700 new stations, making up now for almost 4,100. And the new stations, again, quite a large number of new stations in the Pacific, a few in the Arctic, southwestern Indian Ocean, and Atlantic data in the Southern Ocean, but also process study data in the North Atlantic. In addition to the completely new stations from the new cruises, more TEI data have been added to existing stations, basically in all basins. And this table, which you are not expected to read in detail, but it has a sorted list of parameters with the number of values added since the last IDP here in green on the right. And you see quite prominently dissolved iron with more than 7,000 new data values, now making it up to 23,000, almost 500 values altogether. A whole group of other trace metals has similar additions on this side. More exotic traces, like here the iron isotope data, they actually doubled the value count. We have 1,800 added, now making it 3,300, similar to other isotope data for cadmium and zinc on this slide. So if you have time and you have the slides later, you can look for your favorite tracer and see what has been added. A new thing in the seawater discrete sample data is the parameter unification that has happened. So while GeoTraces does have separate parameters for the different sample system, like for instance, looking at dissolved iron, we have separate parameters sampled with bottle, fish, boat pump, sub-ice pump. These separate parameters, they now have been unified into one single parameter. So in this example, dissolved iron. Here's another example, total particulate aluminium, where we do have actually 5 variants with different sampling systems. All of these 5 have been unified into a single one. And as a final example, neodymium isotope, 3 variants, now just one single parameter. So the motivation, why was this done? This basically was to achieve a reduction in the number of parameters. So if we hadn't unified, we would now have 751 parameters in the data set. After unification, we have 418. And we strongly believe that this will simplify the use of the IDP, and also it will avoid overlooking some of these variants, for instance, fish that cover the surface values. Some people might not even know that this parameter exists and might just overlook and underuse this. Unifying the parameters makes it impossible to ignore. As Bill said before, making this IDP is a real group effort, and I have named here the groups, the committees of GeoTraces, and the individuals that have put a lot of energy into it. I would specifically also add the GDAC, the GeoTraces Data Assembly Center, the development teams for DOR and WebODV. IPO played a crucial role, and also some national data centers in some countries like the US, Japan, France, and the Netherlands. And finally, I also want to acknowledge the continued support, financial support from the US National Science Foundation that we have received through SCORE. Without this work from all the individuals and without the financial support, all this would not have been possible. Okay, so now that you have a feeling of what is in the IDP, let's quickly look at how you can access the digital data. And there are two main avenues. The first one is the bulk download from the GDAC website, which is listed here. When you do this, you will get all the data sets in all the formats. So you basically have everything. This is also the product that has the official DOI, which is listed here. As a second way of accessing that does not require any download of data or any installation of software, we are offering the IDP 2025 via the Web ODV online services. And these services, they include subsetting and extraction. So if you want to have specific subsets of the data, you can do it using Web ODV. Or if you want to do online analysis and visualization, that's also easily possible. And we are now making these services available via three separate web services, just in case any one of them goes down, as we experienced at our institute just recently. The rules haven't changed since the last IDP. An agreement to the IDP fair data use agreement is required, but no registration or login is necessary as before. And if you go through the WebODV Explore route, then basically you have to go into the Ocean panel here, go to Tracer, then to GeoTraces and IDP 2025. Then you will see all the 5 data sets. By clicking on any one of these names, that will open the respective data set. Okay, so the second component, which is the eGeoTraces electronic atlas that is available under this URL, this is now, I have to say, almost industry scale production of section plots and rotating 3D scenes. The new version has more than 2,500 section plots, and it has more than 500 rotating 3D scenes. And in the remaining few minutes, I want to do a live demo that shows you some general operation, but also some new features of eGeoTraces. And I'm hoping that you now see the eGeoTraces front page confirmation. Yes. So the first step, you select your favorite parameters in 2 steps. First, the group. And for demonstration purposes, I will do dissolved trace element isotopes. Then in the second group, you have the list of available parameters under this group heading. So for instance, we could use the iron isotopes. Once you have chosen a group and a particular tracer, then the map will show in red all the sections that have a plot for this parameter, and in blue, the that have a rotating 3D image. So for instance, the iron isotope has quite some coverage. If we go to zinc, we will see it's fewer lines. And just for demonstration purposes, I want to focus on this GP19 meridional section South Pacific. You click on this red label, and that will give you the distribution of that selected parameter. So here, zinc isotope along this section in the South Pacific. the footer here at the bottom of the page has important information. That's what I want to concentrate. First of all, a description of the parameter. Some of the names, some of these parameter names can be daunting, and you might wonder what it actually is. Look for the description, and that gives you at least a sentence of explanation. Next line is the list of data creators that have generated the zinc isotope data along this section. And as a new feature, now all these names are clickable. And I'm clicking on Yojiki. And that will take you to the org ID page of that person. And normally you get a lot of information about the PI, in this case, affiliation and the papers of this person. And all the contributors have these links. The second thing I want to emphasize again is that we have links to the publications for this tracer. So if you want to see what recent publications have been, or what publications exist regarding these data, then you click on this link, and that will take us to the publication database at the IPO in Toulouse. And we would find that there are 2 publications here. One more click on the DOI and you would actually read the paper. So this is extremely useful. And finally, as a new feature, I want to explain this link in the upper right, WebODB session. Imagine you are curious about this parameter, you understand something, and you have hypothesis, and you want to play with this, and you want to go beyond the static image that is shown here. Then click this link, and this will take you to a live data session in WebODB with this parameter. And you could start zooming, you could change palette, you could change the parameters on these axes, just following your inspiration and ideas and hypothesis testing. And let me go back. And finally, as a last thing that always has been available, if you are interested to see a different tracer along this section, you go into this line here, for instance, iron. And if then you want to see the 3D animated image, then you go to the final line down there and you would see the new dissolved iron rotating zine in the Pacific that has the Chinese new data in it, but it also has some other process study and compliant data new since the IDP 2021. And this is basically all that I want to say. In summary, IDP 2025, I think, is an incredibly rich resource. We have tried to make access really simple and create different avenues for access and use it. Thank you very much.
Thank you, Elena, for that. I would like now to introduce Cécile Guilleux. Is a senior scientist and the director of research at the Institut de la Mer de Ville, France. Her research group has made many significant contributions to our understanding of aerosol iron deposition and cycling in the upper ocean. Her talk today is on the release of iron from shallow hydrothermal activity from the Tonga Kermadec arc. Cécile is actually available for questions at the end. Elena, could you please play the video?
Hello everyone. So today we'll talk about dissolved iron patterns impacted by shallow hydrothermal sources along a GEOTRACES process studies transect through the Tonga Kermadec arc. This work is part of CLOEST at PhD, and there is also a paper in GBC published in 2022 in the framework of the Tonga project. So let me take you to the Western Tropical South Pacific, where a huge seasonal bloom, almost the size of France, is observed on a recurring basis. During the Outpaced cruise in 2015, we measured huge iron concentrations in the low basin, up to 16 nanomoles, also corresponding to very high nitrogen fixation rates. We made the hypothesis that iron was coming from shallow hydrothermal sources from the shallow volcanic arc of Tonga. So following this, in 2019, we conducted with Sophie Bonnet another campaign focusing on the bloom area. One of the objectives was to understand the sources and sinks affecting this iron distribution in the Western tropical South Pacific, and to link these patterns to biogeochemical activity and carbon export. So we conducted 9 short duration stations and 2 long duration stations along the arc. The long duration stations include additional short transect from shallow volcanoes to the deep waters. We collected and measured the total dissolved iron in 362 samples to determine its distribution along the transect using flow injection and chemiluminescence detection. So through a water mass analysis, we determined iron distribution due to water mass transport. From the measured concentrations, we deduced dissolved iron anomalies not explained by water mass transport. And finally, we identified the processes behind the longitudinal and vertical distribution of dissolved iron. And I will now go through these different points. So I present first the distribution of iron along the transect. The lowest dissolved iron concentrations were measured in the South Pacific Gyre, with concentrations around 0.2 nanomoles in surface. To the west, in the Melanesian waters, iron concentrations are still low, but higher than in the Gyre, ranging from 0.2 to 0.5 nanomoles in surface. In the low basin, iron concentrations are really high, both at surface and at depth, ranging from 0.8 to 50 nanomoles. And these high concentrations are visible, especially on the arc, as you can see on the small-scale transects performed at the long-duration stations 5 and 10. So we performed a water mass analysis inspired by the work that Liz Artig did for the Atlantic in 2020. And by defining the values and members contributing to the water masses crossed during the cruise, these are the circles you can see on the map, it was possible to establish the theoretical distribution of iron resulting only from water mass transport. And the optimum multiparameter analysis was used to establish the water mass contribution to the distribution of iron along the cruise transect. So these are the theoretical dissolved iron distribution resulting only from water mass transport, derived from the optimum multiparameter analysis, and you see they are very low and homogeneous across the transect. They are representative of classical oceanic profiles for each station, with low concentrations in surface, slightly increasing at depth. And this indicated a low impact of water mass on the dissolved iron distribution. Now this figure represents the iron anomalies with a threshold of above 0.2 nanomoles obtained by subtracting this theoretical dissolved iron distribution to the measured dissolved iron. So what we see is that to the east, the lack of anomalies demonstrates that there is no local source supplying iron to the waters of the South Pacific Gyre. To the west, in the Melanesian waters, except at depths at station 3, there are no anomalies greater than 0.2 nanomole, meaning no local sources either. The most notable anomalies were found in the low basin, particularly near the Tonga Arc. Strong anomalies are visible at surface, particularly near long-duration station 5, suggesting the presence of one or more local iron sources near this arc system. Hydrothermal origin of that iron was confirmed by the detection of other hydrothermal tracers such as helium-3, methane, CO2, manganese, in addition to typical chemical and acoustic features including low pH, low oxygen, high turbidity, and hydrogen sulfide contents. And you can see here, for example, the hydrothermal plume above volcano 1 at station 5 with a strong acoustic signal over the whole water column. So what about those anomalies at depths below 1,000 meters? We observe anomalies all over the basin, indicating a large dispersion of deep hydrothermal iron following the main circulation that is from east to west. There is also the possibility, of course, that those anomalies can be due to additional deep sources associated to the spreading area of the basin. In surface, in contrast to what has been observed for deep hydrothermal plumes, we see here a rapid decrease in the dissolved iron anomalies from the arc to the west over approximately 300 kilometers. And this is likely due to a shorter residence time of surface water masses, of course, compared to deep ones, combined with several biogeochemical and processes at play. So what are those processes behind the vertical and longitudinal evolution of dissolved iron? So what we did in that paper, for a simplified 1D3 box budget, we were able to quantify the importance of those processes based on the observations made at a small scale that represent here a distance of 20 kilometers of the long duration session 5. Of course, I do not have to go into too many details, but in summary, what we found is that almost 90% of iron precipitates in the suboxic layer, that the scavenging, which is here in green, removed up to 72% of the remaining dissolved iron, that biological uptake in orange represented only a negligible iron sink in such high iron-rich environment. And in the upper photic layer, an additional sink of dissolved iron up to 36% was required to close the budget. So this could correspond to a higher scavenging rate in this layer due to the presence of the large proportion of biological particles, of course. But a portion of this sink could also be due to photoreduction. Alternatively, a combination of both processes, scavenging and photoreduction, could explain this additional dissolved iron loss. But these are only hypotheses, and more investigation are necessary to quantify both. So we did not discuss iron ligands in that paper as the data were not yet available at the time. But since several papers are dealing with the organic speciation of iron, explaining how this iron was finally stabilized in the upper layer. So I recommend in particular these two papers of the research topic in Frontiers, recently finalized. I also recommend the paper, the allied paper in Science, more focused on the link between hydrothermal iron fertilization and carbon export. So to finish, these are a few take-home messages. So first, unlike deep hydrothermal vents, shallow vents impact iron distribution over shorter distances due to stronger dynamics in the surface waters, combined with chemical, biogeochemical processes at play. This work also highlights the role of shallow hydrothermal sources on dissolved iron cycle. And despite the small but significant fraction of dissolved iron ultimately stabilized, there is a strong stimulation of the biological activity in the surface waters over a long distance. And finally, there is a need to consider the impact of these sources for a better understanding of the global iron cycle. And this is good news. We have a new project on hydrothermal iron fertilization, including the one from shallow sources, project is named Harvest, and it will start in 2026. And with this, I thank you for your attention.
Thank you, Cecile. And as I said, she's available for questions at the end. So I will like now to introduce Ryan Cloet. He's a postdoctoral fellow at Stellenbosch University and a member of the GeoTraces Early Career Scientist Committee. He earned his PhD in 2021 and has participated in 6 GeoTraces process study cruises. His talk today is on the distribution and cycling of cadmium, nickel, and zinc. Elena, could you please play the video?
Hello and welcome to everyone joining in. A special mention to those present at the GeoTraces Summer School in Cape Town, which is currently going on. My name is Ryan Cloet. I'm from Stellenbosch University, and thanks to the committee for this opportunity, I want to spend the next 10 or so minutes sharing with you some of the work we've been doing in the Southern Ocean, specifically with regards to trace element cycling in the surface ocean. But really, I also want to highlight how the inclusion of the IDP data has really helped us to upscale these observations, and in so doing has empowered us as ocean scientists. I want to start off with a schematic of seasonal ion cycling in the Southern Ocean from Tagliabue et al. Many of us are familiar with this, but it really highlights the key physical, biological, and chemical processes that are at play when interpreting seasonal signals. So over here, starting with winter, we have this high iron stock. It's driven by deep winter mixed layers, which are sustained by strong seasonal storms and turbulence. But we see that as we progress through to spring and eventually summer, we have losses from detrainment and also increased biological uptake and abiotic scavenging processes. So really our idea here is to see how this applies to the nutrient elements. These are elements which are probably less particle reactive than iron. So the idea is to see what are the dominant processes in the seasonal cycling of these nutrient elements. Over here, I'm showing some results from some crossover stations that we did in 2015 as part of the Sussex cruise. The top panels are copper, then cadmium, nickel, and zinc. And I'm showing these crossover stations from the subantarctic zone, polar frontal zone in the middle, and finally the Antarctic zone. And really what we see from these plots is that as we move into the higher latitudes, we see the seasonal signal in the surface really becomes more pronounced and more evident, whereas below in the subsurface, the seasonal signal is negligible, as we would expect, where water mass mixing is dominating the annual cycle. Moving on to these right panels, these are Hovermoller plots. The top panel is weekly chlorophyll climatology, and the bottom is particulate organic carbon. And the top I've shown by this black line where in the year the maximum mixed layer depth is reached. And we can see that in the Antarctic zone in winter, we've sampled really close to this maximum level of mixing, while in the summer, we sample in a period of quite high productivity. So the idea here is this seasonal signal caused by entrainment, or what is the relative importance of entrainment versus biological uptake? This is really where the ideas, we can upscale them with the IDP. This plot is showing all of the Southern Ocean stations that have dissolved and particulate nickel data. They're colored according to their season, and the shapes represent the different zones. And in these panels, I've split the data up into the different Southern Ocean sectors and also shown the data for dissolved and particulate nickel. So these kinds of views highlight a lot of things. First, they highlight the amount of data that we have at our disposal through the IDP. This is all easily accessible. It's open access. There's a range of different viewing, exploration, and downloading options, which make it very user-friendly. But they also help us to identify gaps in the database and also regions where we could really focus in on our research questions based on the data availability. So we are really excited about this IDP release because the group here at Stellenbosch, we have 2 winter cruises and a spring cruise that's being included in this product. And really that's been our goal over the past years, is to really focus on the winter or the transition between seasons, and utilizing the Cape Town's geographic advantage to the Southern Ocean. So looking at this data with latitude now, I'm showing the 4 different metals. Again, the colors are the seasons and the shapes are the frontal zones. And the common trend through all of these elements is we see that these mixed layer concentrations are increasing as we move south, as we would expect in the Southern Ocean, with the upwelling of this nutrient-rich circumpolar deep waters to the surface. But what I really want to highlight here is that because the data in the IDP are of such high quality, they're comparable. This allows for seasonal observations which are at the sub-nanomolar and even below. And this is thanks to years of sampling and analytical developments, but also rigorous review, which allows us to have this confidence in the trends that we are seeing. So if we move to some calculations and visualizing the data in a bit more of a quantitative manner, here I've compared winter and summer seasons from the Antarctic zone, where we see the strongest seasonal signal. I've listed the concentrations, the means for summer and winter, but I've also compared the ratios of the elements to density. And generally, all of these comparisons here are statistically significant. And so the difference in the element to density ratios shows that it's more than just a water mass signal that is controlling these seasonal variations. So what we've tried to do here is estimate the trace element uptake between the seasons and then compare it to the measured difference to see what is the importance of the biological signal in determining this seasonal variation. To calculate the estimated uptake, we have taken the seasonal difference in phosphate and multiplied it by the cellular metal to phosphorus ratio in the cell. Now, typically, these cellular quotas are very difficult to come by and very difficult to match to the phytoplankton community present during our sampling. So again, we can draw on the IDP data, and here I've plotted particulate trace element to phosphorus ratios. I've backed out the lithogenic component, so I've plotted this as excess. That was done using particulate aluminium and upper crustal compositions. And we see here we have different colored lines. The black line is the mean for all the data, and the different colors are related to the different zones. And we'll see that this is really important throughout the metals, because depending on which zone you have this different elemental stoichiometry, which is what we would expect with the changing communities across the Southern Ocean fronts. So I've used the Antarctic zone derived ratios, and what we find is that the biological signal can explain between 70 to 110% with an error of the seasonal signal. And so this is really useful, and we're really looking to build upon these hypotheses as the new IDP comes out. And lastly, just a thank you to GeoTraces, firstly to the leadership to the data assembly and everyone involved, the unsung heroes of the program. The GeoTraces community, I thought I'd add this photo in from the first GeoTraces summer school in Brest in 2017. I was present as a young master's student, and many of you tuning in were there and will recognize yourself and have a nice throwback. But really, it's been such a great community to be a part of, and thank you to all the mentors, the colleagues, and the friends over the years. And then to finally the funding bodies, without which none of this would be possible. So thank you for your attention, and really looking forward to getting stuck into this new data set.
Thank you again, Elena and Ryan, of course. Our next talk is by Jinyuan Lee. He's a visiting scientist at Xiamen University. He earned his PhD at Woods Hole in 2023, working with Dan Repeta. He has been part of GeoTraces community since 2015. As for his master at the University of British Columbia, he investigated particulate trace metals in the Canadian Arctic. His talk today is on microbial iron limitation in the ocean's twilight zone. And Jinyuan is here for questions at the end. Go for it, Elena.
Hello, everyone. Thanks for coming. It's a great honor to be here and talk about our work a few years ago, microbial iron limitation in the ocean's twilight zone. This is a group effort. We have contribution from many collaborators, including Lydia Babcock-Adams, Renee Botto, Matt McGilvan, Laurie Mank, a group of dissolved iron experts, and my advisor, Dan Repeta. I would like to thank NSF and the Simons Foundation for funding support. Okay, I think we all agree that iron is important. In seawater, 99% of dissolved iron are bound to organic ligands, which makes the chemistry of iron very different from nitrogen and phosphorus. To understand the bioavailability of iron and the cycling of iron, we need to start looking at these ligands on the molecular level. There are many different iron ligands in seawater. The first ones we are able to identify are siderophores, which means iron carrier. Siderophores are produced by hydrographic bacteria and fungi. They are well studied on land. There is a library of 300 plus different siderophores with different structures. And here is an example. Siderophores are designed to strongly bind iron through coordination, in this case with oxygen, and to facilitate iron uptake from the environment. Because siderophore production is metabolically expensive, they are produced only under iron limitation. So our goal is to use siderophore as a molecular biomarker to study microbial iron limitation, which in contrast to phytoplankton has never been proved in the ocean. The method to sample siderophore is solid phase extraction. We pump filtered seawater through this cartridge, which retains siderophores and other organic molecules. We wash the cartridge with methanol to recover siderophores and other organic molecules. We measure the sample on liquid chromatography mass spectrometry. The sample will enter the LC column as a mixture of organic molecules. When we pump solvent through the column, different molecules will move at different speed and they will leave the column at different time. So LC is a separation technique and MS are the detectors. The first detector, ICP-MS, breaks down the compound and measures the iron inside. So a peak means at this time, iron siderophore comes out of the LC and gets detected by ICP-MS. So we use it to look for and quantify siderophores. To identify siderophores, we rely on the second detector, electrospray ionization mass spectrometer, which is a soft ionization. The molecule is kept intact for molecular weight determination. We can find the molecular weight by looking for this pair of co-eluting ions with a mass difference of 2 and abundance difference of 15.7, representing siderophore bound to iron 56 and siderophore bound to iron 54, which coexist in the sample. These plots are called chromatogram, and for today, I will only show the iron chromatogram by ICP-MS. With this method, we collected sulfur samples along the GeoTraces GP15 transect in the Pacific Ocean. And here is how the data look like. Each panel is a sample, X label retention time, Y label is iron for the top 3 panels. As we can see, the type of sulfur as indicated by the retention time and the concentration of the sulfurs as indicated by the peak height change from sample to sample. Some sulfur appear as a single peak, and some sulfurs appear as a suite of homologs. So for each peak, we identify them and quantify them and submit the data to the IDP. So there could be a section plot for each of these sulfurs. 2 side notes. Number 1, most of these sulfurs we were able to identify are from hydrographic bacteria, not fungi. Second, not only to iron, sulfur could also bind to aluminum, as shown in this green trace for the same sample. For each sample, we can sum all the peaks for a total concentration, and here is the data. The X label is latitude. We have Alaska on the right, Tahiti on the left. The Y label is depth, and the color is the total concentration of iron sulfurs. The most striking feature of this plot is the high concentration of sulfurs between 200 and 400 meters in the twilight zone. This is surprising because compared to the surface ocean, twilight zone has a lower supply of organic carbon and presumably lower bacterial iron demand, as well as a higher iron concentration. Therefore, the microbial iron limitation was expected at the surface, not in the twilight zone. In addition, this high concentration could be due to either fast production of sulfurs or slow consumption of sulfurs. So to confirm microbial iron limitation in the twilight zone, the concentration data is not enough. We need to measure the sulfur turnover. We had an opportunity to measure the sulfur turnover at Station Aloha, which is in the middle of our transect. To be realistic, the first thing we did was to consult our transect data and figure out which are the sulfurs in situ. Then we grow cultures that produce those sulfurs. We collect the sulfurs, we label them with the rare isotope iron 57 as our spike. So we went to Station Aloha, we gave the spike to the unfiltered seawater, and we incubate the sample in the dark for a few days. Here's the data for 300 meter. X label retention time, Y label is iron 57. The green trace represents the sample before incubation, and the blue trace is after the incubation. As we can see, there are multiple peaks representing different sulfurs, but they all behave the same. They are all completely consumed after the incubation. If we think about the spike, which is iron 57 sulfur, this drawdown could be due to either iron uptake from the sulfur, which indicates iron limitation, or it could be due to sulfur uptake as labile organic substrate, which is irrelevant to iron limitation. So it is important to distinguish these two uptake. Indeed, the iron uptake from sulfur is followed by the release of metal-free sulfur into seawater and the recycling of the sulfur, whereas the sulfur uptake should be destructive. So we can distinguish these two possibilities by looking for metal-free sulfurs in seawater at the end of the incubation. To measure metal-free sulfur in a sample, we add iron to saturate the sulfurs, and we measure the increase of iron sulfurs. On the right panel, the newly added dark blue line represent the sample after incubation with iron addition. So the difference between the light blue and the dark blue represents the metal-free sulfurs at the end of the incubation. And the difference between the dark blue and the gray represents sulfurs we were not able to recover even after iron addition. So we attribute that to sulfur uptake as labile organic substrate or sulfur used for energy. At Station Aloha, we did a depth profile. The dashed line was the initial spike, so we added the same amount to every single depth. Between 200 and 400 meters, most of the spike was consumed after the incubation, and the majority was attributed to iron acquisition. This means microbial community at this depth interval was taking iron from the siderophores. This coincides with the depth interval we saw in the transect where we see a lot of siderophores, confirming microbial iron limitation in the twilight zone. In contrast, at the surface, there was uptake of the spike, but mostly for energy. This agrees well with the low siderophore concentration we find in the GeoTraces transect. In summary, our results provide one of the first evidence of iron limitation on hydrographic bacteria. It also showed that nutrient limitation could extend below the euphotic zone. However, the reason why the limitation occurred in the twilight zone but not the surface remains unclear. Our understanding is, at the surface, iron concentration is low, but nitrogen concentration is also low, and perhaps more limiting than iron at the surface. In the neutrocline, nitrogen increased by a factor of 1,000, whereas iron only increased by a factor of 5, leading to a decrease of iron to nitrogen ratio with depth. Thanks to the IDP, we can calculate the iron to nitrogen ratio in the twilight zone of the global ocean, and we found that in most of the region, the ratio is lower than the minimum required quota for hydrographic bacteria, which potentially leads to microbial iron limitation and siderophore production as a response. Thanks.
Thank you so much, Ying for that. And if anybody has questions, please put them in the chat. Our next speaker is Nate Lanning. He's an associate professor at the University of New England. He received his PhD at Texas A&M University in 2023, working with Professor Jess Fitzsimons. His presentation today is on the use of lead isotopes to demonstrate reversible scavenging in particular rich vales in the North Pacific. Elena, could you please play the video?
Hi, everyone. My name is Nate Lanning, and I want to thank everyone involved in putting together the Intermediate Data Product of 2025 for asking me to speak here today on how stable isotopes can identify reversible scavenging of lead in Pacific particle-rich vales. I've been part of the GeoTraces program since 2016, when I started analyzing Arctic samples with Laramie Jensen and Jess Fitzsimmons at Texas A&M, and so I'm very excited to share some of my PhD work from Texas A&M with you all here today. Before I get into anything, I want to thank all of my wonderful co-authors, Jess Fitzsimmons and Janelle Steffen at Texas A&M, Shuo Zhang and Ed Boyle at MIT, Vinicius Amaral, Catherine Mateos, and Phoebe Lamb at UC Santa Cruz, and of course the GeoTraces program and the National Science Foundation. As I mentioned, this was some of my work from my PhD, which looked at the U.S. GeoTraces Pacific Meridional Transect, or GP15. This was a full depth section along the 152 West Meridian, which ran from the Alaskan coast all the way south to Tahiti. This cruise was from September 18th to November 24th in 2018, which was a low dust season. And all the data I'm going to talk about today was collected using trace metal clean GoFlow rosettes, where we had dissolved subsampling at 0.2 microns. So all the lead data I talk about today is going to be in the dissolved lead phase. And all of our samples were acidified with hydrochloric acid and stored for at least 6 months prior to sampling. So let's get into the lead story. So lead in the ocean, it is a neurotoxin, and it's anthropogenically sourced to the ocean through smelting, coal, and leaded gasoline. There are a few sources to the ocean, which I've indicated in my box to the right as arrows pointing inwards toward the box, and sinks that are arrows pointing out of the box. The two major sources of lead to the ocean are through dust and sediments, with the ultimate removal of lead being scavenging, where adsorption of lead to particles removes lead from the dissolved phase. We can go beyond just thinking about lead and its concentration and its distribution. We can also start thinking about how we can use lead-stable isotopes to be able to tell us something about the lead's characteristics. Specifically, we can think about different isotopes such as 206, 207. You can even talk about lead 208 and 204 as well. But for the purpose of this talk, I'll just be talking about the ratio between lead 206 and lead 207. And that isotopic signature, that ratio, it tells us about the lead's origin. And specifically, those lead isotopic ratios that we see in the ocean, those ratios are set by rocks, ore, and coal of different ages, as well as different gasoline sources. Now, there are two classifications of lead that we want to talk about, being anthropogenic lead and natural lead. The anthropogenic lead that we were concerned about for the purpose of GP15 was anthropogenic lead coming from Asia and impacting the North Pacific. The lead 206 to 207 ratio for those seawater or anthropogenic Asian lead is about 1.14 to 1.18. Now, there is a bit of overlap between anthropogenic and natural lead, with natural ferromanganese lead being about 1.19 to 1.22. Again, there is overlap, but for the purpose of this talk, we can think of anthropogenic lead having a lower 206 to 207 value and natural lead having a higher lead 206 to 207 ratio. So going into this project, what did we know? Well, we knew that anthropogenic lead from Asia is contaminating pristine deep Pacific waters, and specifically through the process of reversible scavenging, it's being transported to depth and as part of the stable isotopes, adsorbing to particles and scavenging, as my diagram on the right shows. So those lead isotopes will scavenge and adsorb to particles, and then be carried down into the mid-water column, where they will eventually reversibly scavenge and desorb from our particles. This is work done by Jingfeng Wu. We know that reversible scavenging is not just happening for lead, it's implemented for other elements such as thorium, protactinium, copper, zinc, and iron. But what we didn't know was how will dissolved lead isotopes react to regions with different scavenging intensities? And what better place than the GP15 transect to be able to try to answer this question? We have our dissolved lead section plot shown up here on the top left, where I have depth on my y-axis and latitude on my x-axis. Alaska is positioned on the right side of our figure, with Tahiti positioned on the left side of the figure. Warmer colors represent higher concentrations, cooler colors represent lower concentrations. The first thing we noticed from our dissolved lead section of GP15 was that we had a large plume of dissolved lead in the North Pacific. And even at depth below that large plume, you can see in the North Pacific, dissolved lead concentrations are elevated compared to the southern leg in the South Pacific. You can see there is a little bit of difference in concentration space. When we started looking in stable isotope space, we saw a low or anthropogenic 206 to 207 signature pretty much ubiquitously throughout the upper and intermediate water column. Okay. However, at very key stations, we actually saw that anthropogenic signal extending throughout the entire water column. Those stations are at station 10 and 12 in the North Pacific, but also at station 29 at the equator. We were interested in knowing what was going on at those stations. We referenced the Aquamodus satellite surface chlorophyll data, and I want to emphasize that where we have high chlorophyll, that indicates high primary productivity and elevated particle load. And we did see high chlorophyll concentrations indicated in the figure to the right at some of those key stations. So at station 29, where we can see we have the equator right here, you can see that at station 29, we have elevated chlorophyll concentrations. And also in the North Pacific, we saw chlorophyll concentrations elevated where we have the transition zone chlorophyll front, or TZCF, which forms at the subarctic frontal zone. And these are regions where we have local upwelling, bringing nutrient-rich water to the surface. And I actually outlined the TCZF on the figure in pink right here. And so at these regions, we have local upwelling, creating a lot of nutrient-rich water and bringing it to the surface. It's forming a lot of cells, so a lot of primary productivity is going on. But then eventually those cells are going to sink out of the upper ocean. As they start to sink, they rain down through the water column, forming particle-rich veils. We needed to confirm that we actually see these particle-rich veils throughout the water column, so we referenced Jim Bishop's particulate inorganic carbon data. So that PIC data did show that in the section plot, which I have right here, that at stations 12 and 10, we do see elevated PIC data throughout the entire water column, and at station 29, we also see relatively elevated PIC data as well. Therefore, our particles are confirming that particle veils at these stations are present. When we did a simple 1D box model, we were trying to understand whether or not the dissolved lead transport could overwhelm natural signals. And what we found was that the vertical dissolved lead transport suggests that particle sinking is going on fast enough to overwhelm our natural signal. So thank you to Vinicius's calculations and Ed's calculations to be able to put together that box model. So what we find is that in regions of high particle loading, there is enough particles that can transport enough of that anthropogenic, that low 206 to 207 signature throughout the entire water column, overwhelming the natural lead 206 to 207 signature that is being horizontally circulated into the equatorial and North Pacific Ocean. We have a nice diagram that shows this idea right here. Outside of the particle veil, where we have low particle loading, we still have that low anthropogenic 206 to 207 ratio that will adsorb to our particles. And again, those particles will sink out of the upper ocean, but there's too few particles to be able to carry a strong enough anthropogenic lead stable isotope signature to set a anthropogenic signal throughout the water column, because that high 206 to 207 ratio that's being pulled in through horizontal mixing is going to overwhelm that anthropogenic signal and continue to have a natural background signature. Unlike in regions of high particle loading, such as at stations 10 and 12, and even at the equator, where we have very high particle loads, we have a strong anthropogenic 206 to 207 signature there, and all of those particles that are in high particle flux, they carry all of that anthropogenic signature throughout the entire water column. And then that horizontal mixing signature is just completely overwhelmed by the fact that so many particles are reversibly scavenging that low anthropogenic 206 to 207 signature at depth. One of the questions we had at the end of our paper was, is this going to happen in other particle veils? And we suggested that it absolutely would. And only the power of GeoTraces is able to show us that that is absolutely the case. So thank you to the GeoTraces GA02 and GA10 cruises that was able to allow Ariana Olivelli to show us evidence of this idea in the South Atlantic as well. So at 40 South, where we see elevated chlorophyll concentrations in the surface ocean, they also found this isotopic feature at 40 South extending throughout the entire water column, where high particle loading is once again carrying an anthropogenic 206 to 207 ratio throughout the water column, where it is eventually reversibly scavenged and setting an anthropogenic fingerprint throughout the entire water column. I'm going to put my final remarks up here on the screen, but I just want to finish by saying and thanking GeoTraces for providing unparalleled opportunities to uncover truly fantastic mysteries of the global ocean. And I want to emphasize that the next large dissolved lead and isotope section is going to come out of the GP17 group, specifically the OS and ANT cruises, where Yadim Kim is leading this project. So we're excited for Yadim and my research to be able to show the next section of dissolved lead. Thank you, everyone, and have a wonderful day.
Thank you, Elena, and thanks to Nate for making that wonderful video. We're going to switch gears a little bit, and now we're going to show you another presentation that is not a research presentation, but instead a new initiative that the GeoTraces community is taking and is going to undertake for the next 10 years or so. Elena, could you please play the... No, before I do that, I will tell you about who is presenting this video. Tom Weber is an associate professor in the Department of Earth and Environmental Sciences at the University of Rochester. He's going to present the video with Zana Chase. Zana is a professor of chemical oceanography at the University of Tasmania in Australia. They're both members of the GeoTraces Data Management Committee and are leading the effort to generate global state estimate for trace elements and isotopes to accompany the final GeoTraces data product. So Elena, could you please play the video by Tom and Zana?
Hi everyone, I'm Tom Weber from the University of Rochester, and I'm joined by Zana Chase from the University of Tasmania to announce a new GeoTraces initiative, which aims to create and release a product called the GeoTraces State Estimates. We're here to tell you what that means, why we think it's important, and how it's going to work. As background, I'll start by defining a state estimate, which generically means our best estimate of the current state of a dynamic system, constructed from data and mathematical models. In ocean sciences, we often encounter these as globally continuous, gridded distributions of a tracer or a process rate, often temporally resolved as a monthly climatology. Familiar examples will be the World Ocean Atlas climatology for hydrography and nutrients, which is constructed from interpolation of discrete data, and net primary production climatologies from remote sensing. So why would we want to construct global climatologies like this for the trace elements and isotopes, TEIs, that we focus on in GeoTraces? This program has amassed a beautiful archive of TEI data that we compile and release as intermediate data products, which in turn see wide use within our TEI community. However, we don't think the data is currently being used to its full potential outside our community. And one potential reason for that is that the raw data can be difficult to get to grips with for non-specialists who may find global climatologies more accessible. We therefore hope that the GeoTraces state estimates, GSEs, will create new users and applications for our findings, of which these are a few potential examples. Applications within the TEI community could include helping to plan future cruises and estimating the global importance of observed processes that happen under specific TEI conditions. In other marine sciences fields, GSEs could be used to provide environmental context, for instance, for rate measurements and omics surveys. They could be used in the climate modeling world as initialization fields, and they might help policymakers visualize things like contaminants and providing baselines against which to assess future perturbations. Finally, we can imagine lots of applications within marine science, education, and outreach. So that sounds great, but where would these GSEs come from? First, we have to acknowledge that our TEI data is still too sparse to simply interpolate the gaps like in the World Ocean Atlas. And instead, our state estimates would need to come from models that have been trained with or validated against our data. This means they'd be highly distinct from the data products, and will stress that they shouldn't be used to replace data, simply to provide a best guess for a TEI distribution in a place or a time that's never been directly sampled, with the added benefit that the models that predict these TEI distributions would provide some process information like estimates of boundary fluxes. Next, we should note that model predictions for many different TEIs like iron, thorium isotopes, and zinc have already been generated and published using both process-based models and machine learning models. In our GSE initiative, our focus therefore will not be on producing new models ourselves, or even on prescribing methods for the modeling community to follow. Instead, we'll simply be aiming to make the most of what's already out there by developing best practices for how to compare and validate the existing models for a given TEI to determine the best estimate of its global distribution. We'll then foster a community effort to apply those methods to as many TEIs as possible and compile the results into a user-friendly product. I'll now hand over to Zana for a little more detail on that process.
Hi, so this slide shows the workflow that we'll use to produce these GeoTraces state estimate product. At the core of this effort are the intercomparison teams. So there'll be a different intercomparison team for each of the TEIs that will produce a state estimate for. They'll be conducting a model intercomparison guided by a best practice guide that's produced by the GeoTraces Data Management Committee. Now down here we have the model generators, and they are the people who have published or maybe unpublished model estimates of different TEIs. They'll provide their model output to the intercomparison teams, who will then conduct this intercomparison. So I'll tell you a little bit more now about how the teams will conduct their intercomparisons. They'll be guided by the best practice guide, and the teams will be comprised of both modelers and observationalists. And they will consider both machine learning models and process models, but these different model types will be assessed in separate model intercomparisons. The teams will assess the accuracy of the models against the latest data in the IDP. And they're going to rank the models using standardized measures that are specified in the best practice guide. And importantly, the process is going to include expert judgment in assessing model confidence. And this is where the observationalists on the intercomparison teams will play an important role. And finally, the teams are going to use the standardized grid and parameter names to make it easier to compile the final GeoTraces state estimate product. So I'm going to illustrate how this might work using thorium isotopes as an example. So imagine that Tom and I, as a modeler and observationalist, have formed a model intercomparison team for thorium isotopes. And we've gathered from the community these 6 published estimates of the distribution of thorium in the ocean. And we've compared each of these models against the thorium data in the latest IDP, and we've used the skill of the models in reproducing the data to rank the models based on their ability to reproduce the data. So then we're going to combine these 6 models. We're going to take their skill scores and combine them to produce the best estimate of thorium in the ocean. By taking the ensemble mean, which is weighted by the globally assessed skill score of the different models, combining that with the model variance to produce the best estimate of thorium. So next, we would provide our best estimate and a report documenting the intercomparison to the Data Management Committee, who will then combine this with estimates of different TEIs into the final downloadable GeoTraces state estimate product. So if this sounds like something you're interested in being involved with, if you want to form a model intercomparison team, maybe you're an observationalist or a modeler, here are some next steps that you can take. So we have formed a website that you can check out here while we'll be providing updates on this effort. And one thing that you should look for is the release of the best practice guide in February 2026. So you should start to talk to your colleagues in your TEI community and start to think about gathering together a model intercomparison team. And if you want to be involved, get in touch with myself and Tom and discuss your project with us so that we can coordinate and avoid duplication of effort. And we look forward to hearing from you and engaging with you on the GeoTraces State Estimate project. Thanks for listening. Bye.
Thank you, Zana and Tom, for leading that effort. Our last presentation is by Phoebe Lam. And Phoebe is a professor in ocean sciences at University of California in Santa Cruz and a former co-chair of the GeoTraces Scientific Steering Committee. Her presentation is on the use of GeoTraces data in teaching chemical oceanography. Elena, could you please play the video?
Hi, my name is Phoebe Lam. I'm a professor in the Department of Ocean Sciences at the University of California, Santa Cruz. There I teach a chemical oceanography class that is required for all of our incoming graduate students. And sometimes I teach an undergraduate elective version of that class for our environmental science majors. What I'd like to do over the next 10 minutes is talk to you about what are the challenges that I feel like are the biggest ones for teaching chemical oceanography and how some tricks that I use to help overcome them, and how we could incorporate GeoTraces IDP when we teach chemical oceanography. So the depth profile is how most of us first encounter oceanographic data. We have depth on the y-axis, some oceanographic property on the x-axis. Here I have phosphate plotted here, and here I have silicate plotted here. These are both from the same station, which is marked by the X, on this transect, which is the GAO2 transect, which is in the IDP. By looking at one-dimensional data, we start to think about the world in a one-dimensional way. And here we emphasize the processes that happen in one dimension. Specifically, we emphasize photosynthesis, drawing down nutrients, phosphate and silicate at the surface. And then as the particles sink and regenerate, we have that return of the nutrients into the dissolve phase. And we are taught that this happens for phosphate generally higher in the water column than it does for silicate. And at least when I was a graduate student, the main explanation for that was that silicate regenerates deeper down because silica frustules simply take longer to dissolve in their journey down through the water column than organic matter does to regenerate. But if you look at a two-dimensional section, then you start to have a much richer understanding of why the one-dimensional profiles look the way they are. So this is the phosphate section along this section here, the silicate distribution along this section here, and the salinity distribution. And what you see are these big tongues of nutrients and salinity. And I plot salinity here because salinity is a conservative tracer and is not affected by regeneration or uptake, and it shows really this tongue of low salinity water indicating Antarctic intermediate water, this tongue of slightly lower salinity than this water indicating Antarctic bottom water, and then this tongue of high salinity water indicating North Atlantic deep water. And then you look at the nutrient distributions and they are very much reminiscent of these major water masses, telling you that the nutrient profiles that we see are not just a product of a one-dimensional biogeochemical processes, but largely influenced from the transport of water masses and the concentrations that they brought with them. So we have these high concentrations of nutrients from the south and low concentrations of nutrients from the north. This rich understanding of the three-dimensional nature of the ocean, I think really can't be conveyed by only looking at vertical profiles. But unfortunately, until recently, vertical profiles was all we had for trace metals. Certainly when I was a graduate student, there were a handful of vertical profiles of trace metals that existed. And we learned about them, and we learned still quite a lot about them. So I plotted here, the distributions of, the vertical distributions of cadmium and zinc to go along with the distributions of phosphate and silicate, and all again from the same station in the North Atlantic. And you could see, maybe not as beautifully as in Ken Brulin's seminal work that first showed this, this relationship, but you see that cadmium looks more like phosphate than it does like silicate, and zinc looks more like silicate than it does like phosphate. So we still do get a lot of richness in understanding, or at least observation from one-dimensional data sets, but really having the two-dimensional, three-dimensional distribution can enrich our understanding as it does for major nutrients. And of course, now we can do that with the GeoTraces IDP. So now we are able to plot these sections of cadmium, these sections of zinc, show them next to sections of salinity, and make those water mass arguments for some of the trace metals. Not all of them, they don't all act this way, but some of these trace metals, especially these two, are beautiful tracers or act, the water masses are really important for carrying and determining the distributions of these two trace elements. But it's not just making these slides that the IDP allows us to do, but having the IDP released also allows the students to engage with the data themselves. And the best tool that I like to use is WebODV. So back when I first started teaching chemical oceanography, WebODV didn't exist yet, and I would ask my students to download ODV and to download data sets, and I didn't really love the process because there was a lot of troubleshooting that I had to do to help them make it work. WebODV is great. It is purely a web implementation of ODV, and it only requires a web browser. So students have access to it. There are really no limitations on operating system or anything like that. And also comes with preloaded data sets. So I often have students start using WebODV and start interacting with ODV using gridded hydrographic data sets, the World Ocean Atlas. So these are gridded, so I can teach them how to draw sections. I can teach them how to make isosurface plots. I could teach them how to connect profiles to sections, to isosurface plots, and get used to the mechanics of using ODV. And then we can go in, when they're already used to using ODV, then they can look at any of these other data sets. And because I'm a GeoTraces person, I like them to look at the GeoTraces data set. And that would be found under this tracer subcategory. And if you were to click on tracer, there would be a bunch of different subsets that would pop up. GeoTraces is one of them. And so you could click on GeoTraces, and then you would have the different IDPs. I made this presentation before the official release. So mine doesn't go up to IDP 2025 yet, but yours will after today. So you could click on IDP 2025 if you want, and then you could choose which subset of data you would like from that. Likely you will want to choose the seawater one and seawater discrete sample. That's where the sort of the bulk of the sort of new oceanographic data is coming out. So you click that, and then after you read and agree to the fair use agreement, you'll see this splash page, which shows you all the stations in which there are data in the IDP. And this is a screenshot from the IDP 2025 from a test version that Rainer Kerley nicely shared with me. So once you have this, then what do you do? Well, if students have already gotten practice playing around with ODV, they'll know how to make sections. They'll know how to make station plots. They'll know how to connect a profile. Vertical profile was a section. They'll know how to make scatter plots, perhaps. And so you can ask them to discover these relationships on their own. And so here's an example homework problem that I've given using the IDP. This was my trace metal section. I think my first section was a nitrogen cycling and star. My second section was, I think, a silicate cycling silica star. And this is my part 3, which is trace metals. And I asked them to plot sections of phosphate, silicate, cadmium, and zinc. I asked them to discover for me what the correlations are, and I asked them to make scatter plots between the trace metals and the major nutrients, and to tell me which are correlated. And the pedagogical goals for all students, I think, having them interact with the data themselves, hopefully gives them a better intuition for the 3-dimensional nature of the ocean. And then for graduate students, I think it's helpful to have them discover relationships for themselves rather than just being told about them. It's good training for their transition to becoming knowledge creators rather than just the consumers that they were as undergrads. So what I would like them to produce for me are plots like this. I've shown you some of them already, the phosphate, silicate, cadmium, and zinc plots from section plots from this section. And then I asked them to make scatter plots. These have cadmium on the y-axis here, silicate, phosphate, zinc on the y-axis here, silicate, phosphate. The color bar just shows depths. And by doing these plots, they can quickly see that zinc correlates with silicate, not with phosphate, and cadmium correlates with phosphate, not with silicate. And then from there, if we've already talked about silicate distributions and silica star and the role of the Southern Ocean in and its water masses and filling a lot of the low latitude ocean, we can start to think about why it is that zinc looks like silicate. We could start to think about why cadmium looks like phosphate, and we could start to engage in discussions of biogeochemical processes, the importance of the Southern Ocean that transcend just looking at data and being given a profile and being asked to remember it. So in conclusion, thanks to GeoTraces, there's been a rapid expansion of trace element and isotope data, and the understanding to go with it, that has exceeded the pace at which textbooks have been able to keep up. But in the absence of textbooks, until we wait for them to come out, the GeoTraces IDP makes this data available to everyone to explore. And having students directly interact with the data with easy-to-use applications such as WebODV, with maybe some guided exploration from you, the educator, helps students to develop a 3-dimensional intuition of the ocean. Happy teaching.
So this concludes our presentations. I really, we are right on time, but before we go, I would really like to thank the speakers for preparing these wonderful presentations. I would also like to thank Cecile and Jin Yuan for being here, available to answer questions. I believe most questions have been answered in the chat, so I don't think we have to stay past this time unless somebody has a burning question. And I will also like to thank Elena for playing the videos and moderating this. And of course, I would like to thank SCORE for all the funding and support for the last, I don't know how many years now, 15 years or so. So thank you, SCORE, for everything and making this possible. And thank you to all the scientists that go and collect samples, organize cruises, analyze the samples and submit the data to the data assembly center so we can create these beautiful intermediate data products. So thank you to all. And I hope to see you soon somewhere.